The other thing I want to say, because last time it didn't really give us much motivation, so I'd just like to say a little bit about like why one might be interested in modular representation theory. So the starting point is basically that groups show up all the time throughout many disciplines of mathematics, and studying a group is really hard, right? Like, I don't know, you can play around with it for a while, but if you sit down and think like, okay, like there's some complexity there which is very hard to deal with, but linearizing them, so via representations, is a fantastic way to learn about your group. And one way you can, I was talking last time about characteristic 0, it becomes really nice. And so whenever you have, say, a characteristic 0 vector space with some symmetry, you will have a group and you can use the tools of characteristic 0 representation theory. So this is very common. But yeah, you sort of lose a lot of information. And in this modular world, you have a bit more information, but it becomes a lot more complex. So I'm going to be talking about this mainly in the second half of the lecture today. But this like modular representation theory, you sort of care about different things. So we're going to start caring about projective modules, something which do not show up in the classical story, which might be a bit strange. But like in general, you should really, like, I would say one of the reasons why everyone should know at least some representation theories, especially of finite groups, is like, whenever there is symmetry and there is linear structure, both of which are very common and very useful, representation theory can tell you something. And often it can tell you something genuinely true. Yeah, is there anything you would want to add? Okay, great. So with that, I'm going to get into somewhat of a technical result, because last time we did mostly formal things. Admitted the Mackey formula was probably the least formal thing we saw. But now I'm going to give you more or less a recipe for computing simple representations of groups using normal subgroups. Right? So, but because this is a recipe, it's a reasonably complicated recipe. So like it'll take some sitting down to get used to. Okay. So as a motivation, like we saw with S4 last week, you could try and induce representations you know from subgroups to get representations of your big group. And then the problem becomes like, how do you decompose them? For instance, if you induced a representation and it were simple, that would be great. So whenever that can happen, you'd want to know about it because that will give you a source of simple representations without having to do much work. So first thing I want to mention is when you're inducing from a normal subgroup, you can say a lot more, right? So we could say, V is some simple in M, then can we compute? So for now, I will phrase this in a characteristic 0 kind of way, but the theorem will actually be characteristic agnostic. But so I'll use these brackets to denote HOMs. So say we induce our representation from N to G, and we want to take its inner product. So in other words, if this is 1, then we know that we found a simple representation. So if you have a normal subgroup, you want to get a simple representation, this theorem, which we're going to talk about for the first half of the lecture, will tell you when you get that, which is kind of helpful. So let's just. So now we've got an induction. Now, by the adjoint property of induction and restriction, what that boils down to on these inner products is a, I guess, inner product adjointness. So this is strict B and B. Okay, and now we're in the situation of Mackey formula. Fantastic. And already we're going to see a simplification that happens because N is normal. Okay, so we're going to take a sum. So now, if we've got a normal subgroup, the double cosets, I claim that the double cosets are the same thing as the left cosets are the same thing as the right cosets. So this is a special statement about normal subgroups, which is just that the left and right cosets coincide. Okay, so this is a bit of group theory. But it almost follows immediately from the definitions. Okay, so double cosets induce up to n. From n intersect, we take a conjugate. We restrict from this conjugate to n intersect conjugate. And then remember, we twist by an adjoint action. All right. But now look, n is normal, which means it's fixed by conjugation. So this sum actually simplifies because all of these are just n. Right? So this becomes the sum over t in t mod n add t b.
Why are you writing add?
So because it's like the adjoint action, it's like conjugation. You could instead write like
You're just twisting representation by t.
yeah. I'm writing add to emphasize that this is like a functor that one does to representations. But yeah, you're just twisting the action by t, like conjugation by t.
Why are you?
Sorry, what?
Why are you saying conjugation? I don't know.
Oh, well, so like if you want to twist the action, your new action is
you're twisting g by okay.
Yeah.
Okay, now I see. Oh yeah. I was confused. Thanks.
Okay.
But maybe if Alex is confused, then others would also be confused.
Okay, so should I repeat the definition of this one, or
Yeah, I mean, add t acts on something. What does it act on? What's add t of b, etc.
Okay, so maybe I'll write that. So yeah, so the idea is, so maybe I'll give two ways of understanding this. So first is if you have b a representation of g, and then b from g to g is an automorphism, then we could define like b twisted by b. So it's b with the same space. So this is what we mean when we say we're twisting the action. So keep the vector space the same, but when you act, let's twist, this is p of g dot b. Right, so given a representation, given an automorphism, you can twist that representation by that automorphism. And that's what's happening here, except except what happens in the Mackey formula is you have maps from the conjugate of h by t, which maps x t inverse xt, and you're sort of going between different groups. So, but when we say like you twist the representation, you generally mean the same group. But in general, this is you have an isomorphism between groups. You can transport the structure of a representation between them. So, yeah, transport of structure is a phrase which I've seen referring to this. But the idea is it's not so hard. You're just sort of like twisting your elements by an automorphism.
But like there's a map from g to aut n.
Yeah. So this was my original definition last time. As in, sorry, in this instance?
In that instance.
Okay, yeah. So in this instance, we can remember that like what makes a subgroup normal is to say that it's fixed under conjugation by the ambient group. So in other words, G, as I was saying, maps to the automorphisms of n, which is just that G and G inverse is always in n. So in fact, this is our like add t. We can conjugate by elements of G and stay within our normal subgroup.
So that map is add, just for add from G. Okay.
Yeah, so there is a little thing to be concerned about here because when you're pulling back, you see if you want to introduce an inverse, but morally yes. Yeah, so the idea is G acts on n, and we can see that it's not G mod n that's acting on n. It is genuinely G. N can act on itself by conjugation, and this is not trivial. But when we do this, I'm saying just do a coset, and this is a little bit of an abusive notation. It really means pick something in this coset and apply this twisting and then observe that it doesn't matter which one you picked, because you are, but so like that's why I'm saying you can sort of twist by elements of this quotient group to get this. So yeah, and admittedly there is a lot going on here. So I would love if someone else could give a question, or Alex again, can have a question. Okay. So, all right. So what does this actually mean? Well, if we assume that this V was simple, and we're assuming that we're in a characteristic 0 setup, so these brackets really do make sense, then this is saying V with one of these is either going to be 1 or 0. Because if you take a simple representation and you twist it, you will still get a simple representation. So, in other words, this inner product counts the number of copies of V that live in this sum. Okay? How many copies of V live in this sum? Well, it's the number of cosets that fix V, right? You could twist a representation, you might get something new, you might get something you started off with. And so I'll write what this is the order of the stabilizer of the isomorphism class of V in G mod N under conjugation action on the irreps of N. Okay. So yeah. So anything in the stabilizer, when you twist it, you'll get something isomorphic to what you start with. That will contribute 1 to this sum. All of the others have no homes between them, and so we get okay. Now, there is a big upshot to this. So like, I've done a bunch of this stuff, and it's like, great, I've got something else. But this is actually useful. This is a really useful statement, because pretend that you knew ahead of time that your stabilizer was trivial, okay? So what does that mean? That tells you that this is 1, which tells you that this is 1, which means you've got something simple, okay? So I'll write that as a corollary. So if I'll say G mod N, maybe I should say acts freely on, as maybe if G mod N doesn't, so let's say if the orbit of the isomorphism class of V, where this is a simple, under G mod N is size G mod N, then this induced representation is simple. Okay, so yeah, so with this you can get some simple representations just by understanding the action of the quotient on the irreducible representations of your subgroup. Okay, so and we can also see that this is an if and only if, right? Like this will be 1 if and only if the stabilizer is true. Okay, so now I'm wondering if I should write this down, but for people who did the exercise, you considered the Heisenberg group with order P cubed. This is the upper unitriangular matrices. Okay, so this is the group of matrices that look like this, where star is in FP. Now I claim that this gives you a recipe to construct all of the irreducible representations of this group. Well, to help. So, and this, will make a lot more sense if you've done the exercise. If not, I mean, you'll just have to believe me with a few of these facts now. So, one thing is you take this group, its center is when these two things are 0. And when you take this group mod its center, you get something abelian. So, in other words, you have P squared linear irreducibles, where linear, one dimensional. And I'll say pulled back from I'll call it H mod CH. Okay, so you're thinking about it first, you may look for one-dimensional representations. Those have abelian image, and then you pull back, you get a bunch of them, you get p squared. But the rest of the representations are not linear, so they're not one-dimensional, so how do you find them? Well, using this, not sure if this is necessarily the easiest way, but you could look at the following subgroup. So, and then you can check that B is normal in H, and that this conjugation action of this quotient, which will be isomorphic to a cyclic group of order P, this acts non-trivial. Oh, sorry, B squared. Sorry. Thank you. And so one can check that this action is non-trivial on B, or more precisely on the irreducible representations of B, it acts non-trivially. When I say acts non-trivially, that means it has orbits which are not size 1, which means that this theorem may be useful.
Are you mixing up? So,
Except now I just realized that you're not going to get irreps this way without doing a little bit more work. Oh no, sorry. Yeah.
I'm just mixing up the groups.
Yeah.
No, just leave that on the board. It's important.
Sorry, yeah.
And then one needs a new example.
That is important. Because this should be. So this quotient is the cyclic group of order P.
Yes.
So then you take cyclic group of order P acting on the irreps of M. Okay, and this is the thing you should analyze. So, and one can check.
What is N?
N is V, yeah.
Oh.
I think N is with notation. Normal subgroup.
I also like N as notation for normal sub, but I like this as like vector space, because it turns out this action is like acting on a vector space. Okay, so what this recipe would tell you is that if you look at this, you see orbits that are non-trivial, then you get irreps for free by invention. And it turns out this gives you all of the other irreducible representations. So if you did this exercise, this is another way to do it, or another way to get these other representations. Okay. So, but this is more for people who have seen this group, have some familiarity with it. Yeah, and I'm going to be doing this a lot, where exercise from the previous week becomes example in the next week of new techniques or something. So, like, the exercise will be very useful to understand the languages. Okay.
Christian, I think I bang on about something.
Yeah, sure.
So I know I bang on about this at IFS, but I think it's really important to ask questions because it's so useful it's useful for you and it's also extremely useful for us. So like, currently I have no idea whether this was comprehensible or not to anyone. And so if people just like ask questions, make comments, etc., it's really helpful, and that's the environment that we want because it's the fastest way and the best way to learn.
Yeah. Like, is there anybody who sort of hasn't seen this group before and doesn't understand, or like, has questions about what I'm talking about here, like how this process would actually work?
And there's no stupid questions.
Yeah.
So, just to make sure, V is abelian, right?
Yes.
Okay, good. So it's irreducible representations that are sort of easy to figure.
Yes.
Okay, so that's
Yes.
a good thing.
And that's a very important thing in this setup, in that like you do need to know a lot of information, right? You need to know the representations of your normal subgroup, and you need to know the quotient, and you need to know how it acts. But in this case, this is abelian, so you know it's irreducible representations. They're not too hard to find. They're all one-dimensional. And the quotient is cyclic of order P, and you can write down what the action is. It's like I'm not doing it here, but it's not like a difficult thing to write down. In some cases, maybe it is, but in this case, you can really write down with matrices and see what this quotient is doing.
As an alternative, can you take on the subgroup to be the center?
That is an excellent question, which I will get back to later in this, because you absolutely can. But let's think like, what happens when this acts on the center? It will act trivially because it's acting on the center by conjugation. So in a sense, this theorem doesn't give you simples. However, the proper theorem will absolutely show that yes, you can do it that way, and it will tell you how to do that as well. So yeah, the center is a really good one to consider because it's sort of like the opposite of this free orbit situation. It's like all of your things are fixed. So then like, what happens? Can you deduce anything? And you can, but it's more involved.
So let's just stick, because this example is so beautiful, so it's worth sticking with it a little bit longer. So we've got p-squared linear irreducibles. Let's imagine Chris's procedure works and produces an irreducible. What dimension would it be? P, yeah? And so how many, let's do the numerics, what do you look at when you see that? Like, what are you thinking? How many irreducibles do we expect?
So I'll do the numerics and someone can interrupt. Okay. Well, we've got p squared of dimension 1. And if we, well, let's assume we knew that they were all the others with dimension p. So then squared. 1 plus and so that means we would expect that there are p minus 1 irreps of dimension p. And that's how I know that I found all of them by this procedure, because one could also count the number of orbits that are big. Like even counting the number of big orbits will tell you that there are p minus 1 of them. And another thing which I didn't do here, but if v and w were different in different orbits, but they were still both free, then this would actually give 0. Like this whole process would just have a w here, and these things would be in different orbits, so they would be 0. So that would give you different irreducibles. Does anybody have any questions about this or this example? Because it is really one.
So like when you consider the irreducibles of the B that you're going to induce, you want to get simple, sort of like P of them will have a big stabilizer and then the rest will have a small stabilizer, and their reductions will get identified because they're lying in the same orbit. And so
yeah.
Okay.
Yeah. And I can even tell you which ones have a big centralizer. So the quotient action on this subgroup only messes with this coordinate. So the ones which have trivial on that action are the ones for which this coordinate or the subgroup generated by this, this, and this acts trivially. So that tells you which ones act trivially. So then in order to get any other representation, take a linear character of this such that this thing does not act trivially, and there you go, you got an error. Okay. So while I erase this, think of more questions about this. I mean, this is a really good example to think about because it illustrates what's going on. And I possibly could have done it in more detail, but I think it is, with this course, like if you're not familiar with the objects, you should definitely do the exercises. And if you don't do the exercises, sort of, I think be aware that you may need to work pretty quick in lectures, because I'll assume that people have thought about these things, they focus a little bit.
Can you just go through that last bit again? So the irreducible representation of V, because it's abelian, there's p squared right?
Mhm.
And it's just the characters on those two coordinates.
Yes.
And then H mod B is CP, and that's acting by conjugation action.
Conjugation.
What is that action on the representations?
So the conjugation action is on B. And then given, say, a linear character, to see what the conjugation action does, you just I'll write it down. So like, you know, say we want to conjugate here. Maybe we'll do an actual example. So say we take the linear character.
So not the board, Chris.
Yeah.
You will talk about it. Yeah.
Yeah. All right. I'll do an actual example. So say we've got AB1. We take the linear character here, which equals B to the A to the B, where zeta P is some fixed root of unity. Okay, so this is a linear representation of this. And say we want to twist it, so twist by, say, we want to twist by this element or the coset of this element. Right? So that means I'll write it like this.
You have to write small.
Okay. So say we're, I guess hopefully one can see this, and this is the same matrix. So we're twisting this and we're applying it to an element. Very explicit. Applying it to this element. So this is by definition lambda applied to the conjugate of this. Now here's where I either can or cannot multiply matrices. Maybe I'll just write this instead of multiplying them out. -1. Okay, so anyone can multiply matrices quicker than me. They are welcome to interject and say what this is. Otherwise, I will think.
Last coordinate will change.
What's that?
Only the B coordinate will change.
Only the B coordinate will change. That is right.
Is it like B minus A?
Yes.
B minus A. Okay, fantastic. 1 A B minus A. And so, what actually is this? Well, this is zeta B. And I could write this as A plus B. Plus B. So now this will be A plus B minus A. This is A plus B. And we can see this is different. So like we've conjugated our linear character and we've got a different linear character. So we know that our orbit will be full side because the group that's acting is cyclical at P.
Once A is less.
Yeah. Yeah, sorry. And then yeah. And you see that it's important that yeah, what is it? B is sorry. This part of the character is not trivial. It's happening. Okay.
Which is saying that it doesn't factor over the quotient by the center.
Yeah.
And
Can I ask a silly low number question?
Absolutely.
So for P equals 2, these are the octonions, right?
So
a group of order 8. So which one is it?
it is D8.
It's D8.
I
Okay.
believe it's D8. I think so.
Okay.
But I'm not fully sure why. But like that's where it lives in my head. I'm pretty sure it's D8 rather. But
Okay.
okay. So now I'm going to give the general theorem which handles this kind of situation. And because it's the general theorem, there are a lot of parts and there are a lot of moving parts. So I'm going to draw a picture. Oh, maybe I'll read that. I'm going to draw a very important picture that if you're like feeling confused, you should consult the picture. So again, n is normal in G. This time B is simple in G. We want to understand the restriction to n. Okay. Right. And so now maybe I'll emphasize characteristic arbitrary. So this is very, very important because we are about to go into a positive characteristic situation where all of the character theory stuff doesn't really work. I mean, lots of basic facts you would love to be true just fail. So you know, you can't, it's very important to like remember when you're leaving the characteristic zero set situation. And this is something which works in both, which is great, but it means the proof is going to be a bit more sophisticated because it won't be just with characters and numbers and such. Like the proof is actually using representations. This representation theory, so it was bound to pop up. Okay, so as a preliminary, I'll give a definition, but I want to give it on a different board.
So Chris, just a silly remark.
Yep.
To Daniel's question, you're right that it's P8 because all of its characters are real, and like that, you can just use the representation theory to show it's P8 and not the quaternions.
Yeah, because this is, well, the real characters doesn't, as in real as in
Like, yeah, non-quaternion again.
yeah.
You know, it has characters that do it.
Right,
one
you
plus
can
one plus
distinguish
one.
them over the reals. Okay, yeah.
All of this group is C2 cross C2, and all elements of all like order 4 subgroups in Q8 are C4.
Okay. Fantastic.
All right, so this is a definition which isn't, I don't think it's standard, but it's very, very helpful just to say it's there. So definition, again, in that setup, W, a simple of n is under B of G. So keyword is under, effectively over, if W is a summand of G and B, which is equivalent to B respectively, say B respectively B over W, if W is a summand of this. So the picture to bear in mind with this is to draw G above and below. Maybe I'll, so G is above and is below it. And you have a representation upstairs, that's B. And you want to understand how it breaks up. And the claim is that it breaks up this. Okay, so I'm going to draw this picture and then explain what this picture is, the one with the theorem. So this is the picture to bear in mind. G over n, you got an irrep up here, it splits up downstairs into things that look like they're being commuted with some e's for it. Okay, so now the theorem, and this is due to Clifford, and this whole picture is called Clifford theory because it's essentially all due to Clifford. Okay, so first is semi-simple. So this is the most important thing for us. Like the other parts of the theorem give you more information, but what's really important in the modular setting is that it tells you something about simple modules of G in terms of simple modules of N. Right? So like semi-simplicity, recall, is that this decomposes as a direct sum of simple modules of N. Great. now I'll explain this picture. There exists W under B, so where this is simple, and integer E, oh, that's a number, such that restriction prime in the G mod n orbit of W, and then E copies of W prime. Maybe I'll say it's better. W prime, E copies of it. Okay, so this is the main part of the theorem. Well, I guess I've said this part's the main. They're all main parts of the theorem. This is a very useful omnibus theorem. There's a lot of parts to it. So the idea is you restrict from G to N, you're simple, you get a sum of simples, and as soon as you know one of them, right? So as soon as you know some W, you actually know all of the symbols. They're just an orbit under this quotient group action. And there may be multiplicities, but all the multiplicities are the same. So going back to this picture, you take this representation, you restrict it to N, it breaks up into E copies of this thing, E copies of this thing, E copies of this thing, and these things are a single orbit under the conjugation action. Yeah, so this picture is really the useful thing to bear in mind. Maybe on this side, that's maybe a W prime. Okay, so now I want to revisit the example that was Alan's comment of the center of the Heisenberg group. So this is these matrices inside the Heisenberg group. Okay, so here H mod ZH acts trivially. Okay, so now let's take some central character, and okay, when you induce it, there will be some n. So in other words, if you take anything of n, there will always be something above it. There might be multiple things, there's often lots of things, but we know everywhere that there's something over it. So let's take our central character and then say that W lies over it. So in other words, this occurs when in the decomposition when we restrict W. Maybe to be consistent, I'll call this thing. Okay, so what does this theorem tell us? It says that when we restrict H, Z of H, we're going to get copies of an orbit of this central character. But this central character, I mean, it's central, so the quotient action is trivial, so its orbit is trivial, so we will just get copies of this central character. How many copies, you might say? Well, this is one-dimensional. Let's pretend we don't know the dimension of these. This is the dimension of the copies. Okay. So now, so now what do we know? We know that we induce, maybe let's, for the purposes of this, let's pretend that we know that it's p-dimensional. Now, there are ways you could tell this a priori, so this isn't really cheating, but this is cleaner if we just pretend we know that it's p-dimensional, so it restricts to p copies of this central character. So then when we induce this central character, then this equals p copies of B plus something else, maybe. So this is the induction restriction thing, right? Like if there are p copies of this in the restriction of this, then there must be p copies of B in the induction of this. Okay, but now if we look at this equality, the dimension of this, well, it's the dimension of this times the index. This is dimension B squared. B, the dimension of this is also B squared, which tells us that we don't have anything else. All right?
Chris, how did you get the induction was that?
Yeah.
Were we relying on having characteristic 0?
Yes. So yeah, wait, so you're using the fact that induction and restriction are adjoints in the functorial sense, but more importantly, they are L2 adjoints for the inner products that are floating around. So in other words, if you take the restriction W, this is the same thing as where this is like number of copies. You should think of this. When these two are both simple, this says the number of copies of W in the restriction of B is the number of copies of B in the induction of W.
So do we need characteristic 0 to talk about the inner product?
Yes. Yeah. So like this example here is all characteristic 0. Yep.
Sorry, silly question. Induction from G to N. Okay, from N to G, should that be at the center?
Yeah. Great. Okay, so what that tells us is that we can, if we just started by knowing that this was p dimensional, another way of constructing these representations would be induce. By this thing, we know that when we induce, we get p copies of an irrep. So then just divide the character you get by p. That gives you your irreducible character. And so this is a way where, like, even though it was central, we could still use this story to find our nonlinear characters. Okay. So now there's more to this theorem, which is important. Okay. So let's see how I'm going with time. All right, well, I'll try to state this theorem in the last 5 minutes. These next parts are not as important the first time you see them, but will be very helpful in doing this week's exercise. So like, and are very worth knowing. It's just, there's a lot of information in this package of data. So, all right, so say W of N, so where it's an irrep, where its stabilizer is S, where we interpret stabilizer by this conjugation action, and we mean the stabilizer of its isomorphism class. Then induction is a bijection between irreps of S still, which equals N dot S over W. And irreps of G over W. Okay, so now I know that this example is in characteristic 0, but all of the theorems as stated here are arbitrary characteristics. So like whenever you see arbitrary characteristic giving you information about simples between different groups, that is like a very big deal. There are very few theorems which let you say that, and this is one of them. In particular, if you're going to look for simple modules, in a group where you understand as normal subgroups, you'll want this theorem. And the last,
You're just like killing off the stabilizer of the corresponding modular dependent, right?
Well-
You're making it bigger maybe?
yeah, so the idea is like, if a symbol up here restricts to like an orbit of stuff.
Yeah.
But instead, if you just, yeah, I guess the idea is instead, if you just had one of these things and you looked at its stabilizer acting on it, you could induce to get this thing. So in a sense, you can always assume that your orbit is trivial by passing to a smaller group. Okay, and the final part, which I'll write over here.
But that still does not be normal, of course, right?
So wait, what needs to be? So
S tilde does not be normal.
no, yeah, S still is normal. Okay. All right, the final part is that, so if you restrict your symbol and you get a symbol, right? So this is the case when everything collapses, there's nothing happening here, then all irreps of G over W are V tensor I star U, for U a simple of G mod N, where G projects onto G mod N by. Okay, so this is saying that, like, if you're in the situation where your irreducible representation of N lifts to an irreducible representation of G, all of a sudden you know all of the symbols. They just pull back from this guy and then tensor. So yeah, so this is like a specific hypothesis, but it does show up. And this is one circumstance where you then get knowledge of a lot more symbols than just what you start.
And that thing is also simple in particular, V tensor pi star U. Or
Yeah, so corollary is that this thing is simple. Yeah, and you would not a priori expect tensor products to be simple.
So if people know, so maybe two comments. The first one is that in modular representation theory, you never expect anything to be semi-simple, essentially. Like that should be your basic hypothesis. And so that first statement is very surprising. Like I remember being shocked by that when I was a graduate student. I was like, now the theorem dropped. Like, just gonna go and find a counterexample, right? And then if people, so some people here like algebraic groups, and that number 4 is the guts behind the so-called Steinberg tensor product theorem. So if that speaks to you, great. Otherwise, don't worry about it.
So in particular, the theorem actually holds for infinite groups as long as the index is finite or something.
Yeah.
Okay, I believe you. Yeah.
Yeah,
It also holds for group, like the Steinberg tensor product theorem is a statement of group schemes.
That's right. Yeah.
Yeah, so like this theorem is it's sort of like whenever you have a normal subgroup, if ever you were given the task of compute the simple character or the simple reps of a modular in a modular setting of a finite group, and you knew a normal subgroup, you could use this machine to make your life way easier. And so this is in one sense in which representation theory can sort of be controlled by normal subgroups. Like there's a whole story in group theory, how you can break groups down into their simple pieces. This is one sense in which the representation theory decomposes along normal subgroups. This is just part of the story, but it's most of the story. Like, yeah, there's a little bit more, but it's not. Yeah, this is definitely the guts of what's going on. Okay, so I think given time, I won't prove this, but maybe I will say, or maybe I'll just say a few words about why this is true. So the idea is we want to, so we know that V is irreducible, and it's a representation. So we're not thinking of characters, maybe I'll use this picture. So within V, restrict it to N and find some simple module. And you'll be able to find some, it's finite dimensional, you just keep going smaller until you get something simple.
Simple submodule, yeah.
Simple submodule, yeah. Okay. That simple submodule will have some isomorphism class, And you want to look at all of the summands, sorry, all of the copies in V with that same isomorphism class. So in other words, you pick a simple, you look at all of the copies of that simple sitting inside your representation. Okay? You may only have one, you may have plenty. That's where E comes from. Okay, so that gives you, and in particular, that submodule is semi-simple because it's going to be just copies of the symbol that you start. One way to see that is there's a surjection in copies of that symbol onto this submodule. Yeah, but anyways, so you will have a semi-simple submodule spanned by copies of the same simple thing. It may not be a summand yet, you don't know that. All you know is that it sits inside. Right. So then you use the fact that G acts on V to say, well, given any element of G, I can multiply this submodule by that element. Right? So you take G times this whole subspace. And then the claim is either that subspace is exactly what you start with, or it's something completely disjoint. So, yeah, so when you consider G dot, we'll call it W bar, this is either equal to W bar or they don't intersect at all. And the idea is, this is because n is normal, this is an n submodule, it will be semi-simple, and it will consist of copies of the twist of W. So it will depend on whether this G fixes the isomorphism class of W or not. Okay? And so then the idea is you take all of these different translates of this thing. So you have the subspace and you take all of these different translates and you take the direct sum of them. There's a map from that to V, and you count dimensions and see that it's an isomorphism. Well, you count dimensions and then you use that V is simple. So this is really like you build a decomposition into symbols by hand almost. And this isn't something which I've really seen anywhere else. Like this feels like a very representation theoretic thing to do to like, I don't know. I've only seen this where you literally build the semi-simple decomposition rather than appealing to something. But Jordy may
Yeah, I think that like if you just want one, there's a much simpler argument. So you take your representation and restrict it down to n. Now there's a simple submodule inside that. Now there's a basic lemma in representation theory, which says that a module is semi-simple if it is a sum of simple submodules. So if it's a sum, like, you know, if I have a module, if I can show that it's a sum of simple modules without the sum being direct, it's still semi-simple. So take this thing, you restrict down to n, you find one simple, you look at all the G translates, and it's very easy to see it's the sum of all the G translates. It's not the direct sum, it's just the sum. But now we apply this basic result and get to the semi-simple. Yeah. So roughly, I think that I take this restriction, restrict it down, and now it has this simple submodule, and it's covered by like heaps of different translates of this thing. And that's everything by simplicity.
Does that use finite index?
I think so.
Maybe there's an issue with sums and products or something. I can't.
I mean, it might be that you just need finitely many, because when there's finitely many of them, it's like the quotient of the sum of finitely many simple objects will still be semi-simple.
Yeah.
Maybe that goes wrong, but yeah. But all right, so we'll have a break. I realize that this is like a big theorem, so it's very much worth thinking about. If you have any questions, come and ask me. Like even if it's, do you have a good example that wasn't that one or something like that? It's worth understanding. But yeah, we'll take a break for like 7 minutes, and then we'll get on to some easier things.
Is there any chance that we'd like to go? Yeah. Is there anything you can write them? Oh, cool.
Absolutely.
Yeah, that's right.
Okay, so Jordy and I gave different proofs. I think Jordy's proof is simple. So the idea is get a simple submodule complete. And then imagine that you can translate it by elements of G. So that is what I'm doing, but he's doing it in a bit of a like less sophisticated way, which just gets this in an easy way. So the idea is PW is a simple.
You've got to do the last two want to sleep at night. So it's actually like two shots.
It's okay if it's like you're in the same,
So then,
you're in a small area.
because he is
But
simple.
I mean, we'd be in a small area.
These subspaces is a G somewhat because you're just
I'm sorry.
why G is this. You just get some
I mean,
models.
I'm not, it's fine, like,
And so then you know that
there's
gives
various
every-
things that can like.
So then the idea is to take
Like, like, you know,
the direct sum
for a couple of days, you just wake up at 3
of all the
started boarding rise.
you don't know.
I mean, that's definitely worse.
And
And then
that's the object.
like for about a week, she's like really unsettled in the evening, like crying a lot.
And then
also
because of this is semi-simple. And then the dilemma that Joseph said, the quotient of a semi-simple thing is.
Yes, like they don't, like pain is like such a weird experience, right? If you have no explanation of like that it's gonna stop at some point, that it's probably just like some disease.
I would say this is
Like
like
yesterday, we went for a time and she really had a breakdown. I think because it's cold, it's what I was
dealing with acting up, no?
Yeah, it must be so hard if you have no idea like that this is just so bad, then it's all stop. I don't, you don't want it or have to.
So my proof.
The other thing that's funny is that like, and then I walk up and she's just like totally killed. What just changed? Like,
So this particular we stabilizes the isomorphism class. That was really this because we sort of the sum of all the things.
But then this E is equal to.
I think like there's
It's full subspace, but we play with it and we stabilize them, we mix them around. I have to write that in. You can, it's quite interesting about this. For instance, X3 independent and restricted. Because they have a resize of it, some regenerate. Like stacks. And not get something like that. So.
Yeah, and I don't know experience of like being confused on something and then like thinking about it for a bit on my own and then like, realizing it's obvious. And for my own, it's like I'm a bit. It's just shout out the words and I'm happy to wait. See what it means.
If there is a scenario result, where like.
This one.
Yeah.
I would say that would be
How do you?
when you're there,
How does that work?
I want to help you.
How do you like do this argument?
I think the truth is just completely independent of grouping finite. If you need this finite index,
But if it's not, oh, okay, but so what if not points, what if it's not?
so my key example, the first time I saw this theorem, it's not infinite group of index. But relating the data is old, it doesn't exist in the factor, it's index 2. So somehow we always double them with a sign, because in this case, it's
And I kind of believe it if you have like points, like you can say like, oh, it takes like elements and quotient. I guess maybe you have has to be something from like a finite index type of thing, and you have to.
that's right, yeah.
So you, okay, so you have this the translate argument, the part that's but okay, so it's not true if it's not finite index.
I think it's wrong in practice.
Yeah.
But I'm not one of them. Certainly the truth I think. The honest proof that and some are really bad.
But it is true that if you have something is an infinite sum.
Yeah, it's like the idea is, yeah,
then it's
just
simple.
like
Then it's gonna be simple. I know that argument doesn't rely on having a finite. Also, it would be a finite sum, right? Think about it, it's a finite thing. You're saying infinite sums, so guess what? You're a finite sum, so just choose. It's gonna choose finally many of them. So that part's not a problem. You're starting to dimensional, it's assuming your representation is right. But the translator is
really,
yeah,
so I really have to do it.
maybe you're like.
I think this is wrong.
I don't know.
I kind of feel like if it takes G to be the CNN, then any finite bit will be somewhere.
Yeah, okay.
And this was a statement.
Then you're saying this.
We can't get it wrong.
But it won't be one.
Sure.
Also, that's, yeah, that's totally.
How many normal figures are we on?
But I think it's wrong. I think clearly just say it's wrong. I would careful enough to not distinguish between.
All the questions are right.
And I've never. But I also don't. It looks like.
But if you're a simple module, guess what? Choose finally, you only need finally many of them. Right? That's very clear.
Also depends a bit on your definition of what finite sum. So I think it's just here with my definition of finite sum.
Yeah. I'm starting with a finite dimension module. The module is finite, so it's very.
Right? Yeah.
If you're adding over, you don't need finally many of them. Take those finally many. By the same reason.
If the representation is not finite, you're asking me to know.
Yeah. Yeah, I'm assuming I have a finite dimension module for like an algebraic group. But the thing that's like clear to me is that, like, let's say I have a scheme, take a normal subgroup scheme, and take a, this whole translate argument, I get nervous about it.
Yeah, I would.
I guess it's starting for you to be emailing me, you know, the draw. I mean, this board.
Yeah. I don't know how you would mimic that. I'm trying to think how you
The standard example is what was talking about with special.
Yeah.
But it might be a bit fishy in the characteristic or something, maybe, I don't know.
Simple.
The doubling happens for Davis 1-2, and I'm not sure what happened to character 2.
Yeah. I'll take the orthogonal group and like, I guess. You have
No, I just wanted to say, it still works for but maybe the classification gets a little bit different because so it's not character. Okay.
So this is the
oh, how it
this is saying
Those conjugates might be able to stay in the belt. There's certain differences.
Yeah.
So I'm not sure how that is. Competitive is, I'm not sure how.
But you're scheme that can work. Yeah. This sort of twisting your representation.
But I would also expect it to be well known.
yeah.
Clifford must have been the
What?
The Clifford, the original paper must have been in the script.
Is that what they were just like?
Yeah, someone would have just.
Two-dimensional. Turns out that this is the sum of two linear representations, one of which I'm going to say nothing is well written, where this is the phrase like that divided the square root. Which is what we use.
Yeah.
It's like then. If I take everything down, you can fall off. So the fiber is not just something to- Exactly. It's not these are-
And there are a lot of it's helpful to do with like sit down with an actual example. Like the one which was on the middle of the it's still there. Yeah. This is like an example. This actual action. There's a lot of moving parts. It's doing this for S3.
Yeah.
Most.
Like when you read this.
So in this instance, they're using numbers. And it is a literal number. Like, something. And so like, this is just saying it eats this group out and it spits out this number. That's a group of all this. Yes, but that decomposing things into products characters is also really how to get the constructors. So like, is that, and that's why I wrote it like this, slightly better, right? This before. Yes, so like, yeah, here is a single random. Single random this.
Someone who was Republican. Other claims they make.
You might want to continue.
Oh. Yes, oh, yes. I indeed do want to continue to go for the definition.
Okay, fine, yeah.
Pick that up now. All right, so now we're going to get into the name of the course, which is modular representation theory. So we'll occasionally reference characteristic 0, but for now, the standing assumption is that the characteristic of the field divides the order of the group. Okay. So I've sort of said this a few times, but the main problem or main difficulty is that rep G is not semi-simple. So not everything is a sum of simple submodules. And I'll give an example. So take P equals 2, and your group being the cyclic group of order 2. I'm going to write down a 2 by 2 matrix that squares to the identity. Okay? And take, say, if tau is the non-trivial element of C2, this is our representation. Okay? So when you square this matrix, you get the identity because you are mod 2. Okay? But now this representation is non-trivial, right? This is not the identity matrix. But if we call, maybe let's call this one V, we have a submodule sitting inside V, which is the trivial representation, which is the submodule spanned by the first vector. So this is the span for the E1. And when we compute the quotient, we also get the trivial module. So this is spanned by coset B2 bar. But this is not the trivial module, so already complexity has arisen. In simplest group, the lowest prime, things are getting complicated. And this is a massive source of complexity. which for the next few lectures, we're gonna try our best to avoid or get around it or see if you can make everything semi-simple and still get something out of it. So yeah, so this, and because we have things like this, we're going to be entering the realm of homological algebra, which deals with exact sequences and derived functors and that sort of thing. We won't get there for a few lectures, but like, this is a warning. The course will get more homological, so you think about homological algebra hopefully before it shows up. You can ask me if you want that to be made more precise, but like, consider this a warning that things are going to get more homological algebra. Okay, but let's pretend that we want to, not even pretend, for this lecture we want to ignore all of the homological complexity. So let's just say we're looking for simple modules, right? But now we're simple, we're in characteristic B. Okay, so I'm going to give a theorem, which I believe is due to Brouwer, which tells you the number of simple modules, mod P, right? We knew in characteristic 0 it was the number of conjugacy classes, and that was kind of helpful because that could tell us when we found all of them. Okay, so theorem is number of simple KG modules equals the number of, it's called P prime conjugacy classes. So where the conjugacy class G is P prime if G has order co-prime together. Okay, so this is really nice. I mean, we still have a description of the number of simple KG modules. It's still something that you can compute by hand without too much difficulty. Just know the orders of the elements in your mind. So for instance, let's compute all of the simple modules. Example, P equals 3, G equals S3. Okay? So first off, can anyone tell me one simple module? Trivial, great. And anyone tell me another simple module? Sine. Fantastic. All right, great. Now, what are the conjugacy classes in S3? There's the trivial one. That's order 1. Transposition, order 2. And the 3 cycle, order 3. In particular, there are only 2 P prime conjugacy classes when P equals 3, which means we've found all the simples. Fantastic. What could be more easy? Find the simples of Sn mod P. Okay, now let's give another example. So, all right. P is a prime, P is always a prime, and I'll say G equals a P group. So this is a group of order P to the n. Okay, so now every non-identity element in this group will have order 0 mod P. In other words, P divides the order of every non-identity element in this group. Okay, so what this means is that we only have one P prime conjugacy class. Conjugacy class. In other words, only one symbol. And I reckon we know what it is. Great. Awesome. This stuff's easy. We've already done 2 examples. But let's note, if this looks like it's easy to describe, it's only because we asked for simples. So for instance, if we took C2 cross C2, a group of 4 elements, and you tried to say classify its indecomposable modules, mod 2. Right? So simple things can't be broken down at all. Indecomposables can't be split into direct sums. I believe this is already intractable as a problem. Like,
I think that's still
P is
doable.
bigger than 2. P equals 2 you can do, but I think
Yeah.
P bigger
C2 cross C2.
C2 cross C2, CP times CP for P bigger than 2 you can.
Oh, okay. Well then how about, or we could say C2 cross C2 cross C2.
Yeah.
That's, we're off the deep end. So like,
So the client for group has infinitely many, but you can classify.
oh, but you can classify it. Oh, okay. So it's like that edge case where it's not finitely many,
Right.
but it's not completely. Okay. Fantastic. But so this should give you an idea that it is deep waters, like trying to classify things which aren't simples can be very, very hard in this instance. Some would say it's so hard that you shouldn't try. But I wouldn't say. Okay. So now,
One thing I forgot, does this theorem need algebraically closed?
yeah, I think
so.
my standing assumption is algebraic.
Ah, okay.
Yeah. Like, yeah, I mean, there's beautiful things that can be said. It's not algebraic of those, but yeah. Okay. Now, we could also ask for P equals 2, still dealing with S3, but now our list is insufficient, right? Because the sign rep, when plus and minus 1 equal one another, that is the trivial rep. So, got 1, but now we can, I claim that if we remember that other representation, the non-trivial symbol, was defined as, right, so V was the functions from E1, E2, E3 to K, so from a 3-element set to the ground field such that f of E1 plus f of E2 plus f of E3 equals 0. This is still a valid representation, mod 2. And I claim that it is still simple. But to show that, you may need to do some work. Or you could use theory int for exercises, but like you need to do more work basically to show that something's simple, because it no longer follows from numerical criteria in terms of characters. So, but for p equals 2, we can still classify the errors. Okay. So now I'm going to talk about a completely new phenomenon, well, new in some respects, which shows up in characteristic P representation theory of finite groups, but shows up basically in the representation theory of everything. If ever you have like representations of something which are not semi-simple, you'll want to consider projective representations or projective modules. Sometimes they may not exist, but in general, like all of this emphasis on simples, sort of, you also want to think about projectives. They're very, very, very useful. Yeah, like there's some very beautiful duality statements that we'll come to involving projectives and simples in this course. And like, for instance, in this picture, if you know your projective modules, you can know your simple modules. But I should tell you what a projective module is. It's just a class of module, a class of representation. And I'll give the definition specific to RepKG. People who think in terms of abelian categories and haven't seen this before should be able to write down what this is in general. If not, don't worry. So P in RepKG is projective if. All right, so there's a lot of equivalent definitions for this. I'm just going to give a few of them and explain why they are the same. Okay, so one way is that it lifts along surjections. In other words, if you have a surjective map from n to m and a map from P to the base, then you can lift it. So there exists a lift. Okay, maybe more tangibly, that there exists a module Q such that P direct sum Q is isomorphic to some copies of a free module. So another way of defining what a projective module is take a free module and take some ends of it. Okay? So in particular, the free module is a projective module. Right? And you can check that the free module satisfies this property. Okay? So next is that any short exact sequence 0 k to m p splits. That is, there is a section of this, and m is a direct sum of k and p. And then the final one is the functor, which takes in the representation, basically the Hom functor from P, the thing which detects Homs from P, is exact. So if you haven't seen what an exact functor is, I don't think, well, I don't know, you apply your functor to a short exact sequence and you get a short exact sequence. It's not obvious, why this is so important, but all of these things are equivalent and all of them define projective modules. Okay, so first off, maybe we should see why one of them is equivalent. Like, yeah, so or maybe let's prove one of these implications. They're not, none of them are too tricky, but I'll prove one of them. So let's see why this implies this. Okay, so for instance, we have surjective map onto P. You take P, we could take the identity map. This tells you that there exists a map up here, which such that this diagram commutes. In other words, that this splits, and then the general splitting lemma of given categories tells you that this is a direct sum of P and K. So, and all of the others are, okay. For this one, pick a surjection from your free module onto P, then split it. There you go. Like, it's not too hard to show that these are all equivalent. And if you haven't seen projective modules before, this is a good way to sort of get a feel for them. Okay, so does anyone have any questions about the definition of projectives? Okay. So now I'm going to explain why, they're sort of dual to simple modules. Like, why I care so much about projectives. So the good thing is, in Rep G, you can classify indecomposable projective modules. So there's a very satisfying way of doing this. Okay, so theorem / definition. Well, it's more of a theorem, but so every M in KG has a what's called projective cover. Okay, so this is some projective module surjecting onto M, well, that's pi, which is characterized by, so this isn't a universal property, or not really, but it has the same flavor. Okay, so first, AM is projective. Right? And then AM onto M is surjective, but for any proper submodule N inside PM, the induced map is not surjective. So the induced map from N to M is not surjective. Okay, so how should one think about this? this is, you're given some random module, you can find a projective mapping to it. And this is saying that you're doing that in like a minimal way. So, right, so this is saying that any submodule, like, in other words, if you want to hit M along this map, you have to use the whole projective. You can't use a submodule. And it's, at the moment, it's not obvious that this exists, that these things with these properties exist. But let's just think first off why this might be unique. Okay, so this isn't a fully fledged universal property, but I'll give an argument for uniqueness. So say we've got Pm prime and Pm. All right, well, this is a surjection. Well, one thing you can do with projectives. So this lifts to here. And because this thing, like no submodule of this surjects onto M, that tells you that this lift is actually surjective, right? Because if this thing lifting up to here didn't hit everything here, it couldn't possibly surject onto M. Okay? But now you've got, two finite dimensional vector spaces and a surjective map between them. So it's mathemorphic.
Did that make sense?
Would anybody like me to repeat that?
But I mean, is it true that a surjective map between finite dimensional vector spaces is nice and interesting?
Sorry, that is not true, unless they have the same dimension. So if you have a surjective map between vector spaces in both directions, then it's true. That's good. All right, so this is an argument for uniqueness, right? Like, if these things exist, then they are unique. And the problem is, like,
but just maybe it's important to point out that this is a unicity up to non-unique isomorphism.
Yeah. So it's not a canonical thing. It's just this is something that exists, but there's not a canonical isomorphism between them. There's always an arbitrary choice here. But I don't know of enough examples where this specifically is a problem, the non-unicity.
Yeah, I mean it's a really genuine problem. And yeah, I guess I really think about it like there's certain objects in maths where, if you have it and I have it, we have literally the same thing, we can identify them. But then there's certain situations where we have the same thing, but there might be many different ways of identifying them. And this is one of those situations. And I remember when you first start hearing these things, you think, well, it's just the same thing. What are these people going on about?
Mm.
But like actually at some point it does start to bite you.
Mm.
And this definitely bites you.
Do you have an example of when?
When it bites you, well, often like you, for example, you've got your two objects and you produce the map. And if your two objects are totally canonical, you've got control over what that map is. But if your objects are only up to isomorphism, you have no control over what that map is.
Like you can't define maps functorially in this way, I guess would be a way to say
that's
that.
a really good way of saying it.
And if you're not defining your maps by a functor, then like, what are they? How do you get a handle on them if you're not constructing? They're just sort of
like that map that Chris wrote down there, that one. It's a rather mysterious thing. Like you don't know what it is, you know it exists. And it's hard to argue with. It's hard to say this map, blah, blah, blah. Like an example might be you might have another module and then you might have a composition. You might say this composition satisfies property blah. It'll be very difficult to actually do that.
Okay. So if you had like if it said there exists unique in property 1 on the right board, would that fix things?
But then those won't exist.
Yeah, as in that's not
exactly.
true.
That
That's
would be
not
a
true.
genuine universal property. Like if it's a unique, like a free module.
Yeah.
If you have a set X, I have a set X, we build a free module on that set. We know these are the same thing with the canonical map between.
Yeah, I know what canonical means, but like the uniqueness is the significant part, right?
Exactly. Yeah.
Because it's only one way of identifying.
There's only one functorial way.
Yeah.
Like the definition gives us the map.
One like natural way.
Yeah.
It sounds like the same problems that people have with that axiom of choice to me. Like, I don't really understand why you can't just sort of hand wave the problem away by like saying just choose one map and fix it.
Well, but like you could choose one map between some objects, but then you need to choose another map. But then, might those agree with one another?
Oh, okay.
Not necessarily, like, it's not even saying that you can make everything agree and it's an arbitrary choice. It's like, you may not be able to make everything, you may not be able to make all of these arbitrary choices line up with one another.
Yeah.
So that's another way in which projectives like harder to work with. It's like, the map exists, but you have no idea. You can't really use it. Well, you can use it for lots of things, but only that it exists. And yeah, I want to say that like these exist in our situation, but this is not a formal argument. Like this is not to be taken for granted. For instance, in similar situations, for like modules over a finite dimensional algebra, these projective covers exist. So projectives always exist in module categories, but projective covers always exist in module categories. But the dual notion of like an injective hull, where you reverse all the arrows, doesn't exist in general. So like this is and you can sort of get a feel for the fact that this is not a trivial thing by the proof. The proof's reasonably involved. But I can at least tell you the idea of the proof of how do you construct a projective cover. Take any map from a projective onto your thing, and then look at a minimal submodule projecting onto your base. And then prove that that is in fact a projective cover. So a priori, that thing need not be projected. But in fact it is, and it has this property that characterizes projective covers.
Maybe just a comment on something you just said. So I think a really nice example to keep in mind is that projective covers do not exist in finitely generated Z modules.
Inject. You're talking about
No projective covers.
So we have projectives, but no projective covers.
This is something that when I first heard it also sounded wrong. So it may sound wrong to you, and think about why. Well, maybe I'm wrong, but I'm pretty sure I'm not.
Yeah.
So
And like what would happen if one tried to run this argument for the, this is a free Z module, so particular is projective. You're not going to find anything smaller surjecting onto Z mod 2, right? But I claim that there's no smallest submodule of this thing which surjects onto Z mod 2. For instance, Z, like PZ inside here is a valid submodule, but it always surjects. So, there's no minimal one. Like the thing which makes this theorem work is that you could sort of have no infinite descending chains of submodules.
Right. So you're also saying here that the projective cover is finite dimensional because in general that doesn't need to happen, for example.
Oh, I mean, for me, everything is finite dimensional.
Right. So no, I'm just saying for an infinite group, they don't need to be finite dimensional.
Do they exist? I mean,
They might exist, they might not exist.
Right. So like you could have a projective cover where you have to go up to infinite dimensionals. Yeah. All right, so now I just want to give some properties of these. Oh, and maybe I'll give a picture. So when I was saying there's like a duality of sorts between projective modules and simples, the way that works in one direction is take projective cover. Okay, so properties. The first one is that the projective cover of a direct sum is the sum of the projective covers. Great. And then, so then any projective P is a projective cover of well, I guess one would say any P, it's projective cover along the surjection of P mod the radical of P. So maybe so this is the Jacobson radical of this ring. But if you haven't seen that sort of thing before, you want to think of this as defined to be largest semi-simple quotient. Of P. So, in other words, given a projective module, you take the largest semi-simple quotient
Wait,
and
with a bracket?
this is the Jacobson radical of Kg applied to P,
I would like it.
which is the radical of P. So, and this second theorem is like a little bit deceptive, because it's actually very, very it's a very important thing which is worth thinking about, because what this says is that given any projective, you get some semi-simple thing, and then by the uniqueness of projective covers, you could recover your projective if you knew what that semi-simple thing was. And from this first thing, if you knew that your quotient, the thing that you're covering, breaks up as a direct sum, you know that your big thing breaks up as a direct sum. So what this says is that, I'll say this corollary, but it requires a bit of thought, is that any projective is a direct sum of PS for S simple. And this is unique. And I'll say that the sum ends are uniquely determined. Well, the sum end multiplicities. Correct? Is not determined. Right. So in particular, a corollary of the corollary, maybe I'll do it here. Okay. So this tells us that we know the indecomposable projectives. Corollary, indecomposable projectives are in bijection with simple modules. All right. And this direction is projective cover. And this direction is semi-simple quotient, or largest semi-simple quotient.
And just to be anal, in the composite projectives, up to isomorphism. And any projective is isomorphic to.
And so, in particular, you take an arbitrary projective. If it breaks up as a direct sum, then it's then this tells you that your quotient breaks up as a direct sum, and so it's the sum of two projective covers of the direct sum ends. So these two things together in this corollary and this corollary, but it takes a little bit of thought. Okay.
So this is really beautiful because now I can point out that in the semi-simple case, they're actually the same.
Yes.
And that's obvious from your diagram. Okay. It follows from your diagram.
Yes. Yeah. So in the semi-simple case, these aren't the same. Another way of saying that is that simples are projected in the semi-simple case. Or alternatively, everything is semi-simple. Okay. And so this is, I think, really nice because it's on one hand, you have simple symbols. On the other, you have projectives. Every other module is sort of in between those two things. And you can sort of analyze, I don't know, you can sort of get away with not thinking about modules which aren't projective or simple, somewhat. because everything is sort of between both. I guess you can sort of see two sides of the complexity spectrum, because projective modules are very simple in some respects, and simple modules are very simple in some respects, but the respects in which they are convenient are quite different. And this tells you that there's like a duality between it. So, okay, so does anybody have any questions about these statements or this like picture? Because this is definitely like a picture to internalize rather than just resolve.
You just say again in characteristic 0 why is it clear from the definition that simple things are projective, or only through this theorem?
You could show it. I would say it follows from Scher's lemma, or it follows like the idea is if everything is copies of simples and you have a surjection, like it's equivalent to sort of finding maps back in vector spaces. Another way of saying that it behaves just like vector spaces, and so it's an equivalent problem to showing that like any vector space is projective, which depending on how you think about it may or may not be trivial, but like it's an equivalent problem to that.
Maybe point 2 on your list was that projective modules are direct summons of free modules. In the semi-simple case, just everything is a direct summon of a free module.
Oh yeah, true. Yeah, that's a good way to see it.
Chris,
Yeah.
Does this hold if like an associative algorithm is an algorithm, or do we not that as absolute rules?
I think someone can correct me if I'm wrong, but I believe this holds for finite dimensional algebras. You still have projectives, you still have simples, you still have projective covers. Yeah.
I think you should do an example of the simple corresponding to PG.
So Chris, what's the projective cover of the trivial modular P group?
That's a good question. So I think your question was also good.
But I thought it was the same question.
It's the same question.
Okay, yeah. So I didn't hear the word figure. So I was like, oh no, in general, like, yeah, okay. So let's think about the G of P group, characteristic P. Can we find any projective modules? I claim that we can. All right, so we can find a projective module, and then the claim is that this is indecomposable. Okay, in other words, AKA is the projective cover of the trivial module. Okay, so how might we see this? This would be how I would see it. There's possibly an easier way. If it's split up as P plus Q, these would also be projective covers of there would be projective covers of copies of the trivial module. In other words, which would imply that the HOMs from KG to 1 would be the HOMs P plus Q to 1. So the dimension of this would be at least 2, because P is the projective cover of some copies of 1, Q is the projective cover of some copies of 1. In particular,
so you're using the fact that we know that there's only one simple module.
Yes, yeah. That's the main factor. There is only one simple module. So which implies that P for Q must be 0. 0, since this space is one dimension. So this is a useful thing to think about in that for a P group, the simple, you can describe it. The projective, you can describe it. Everything else, who knows? Like, there's a lot of complexity when your modules are not simple or projectives. And sort of the whole theory is quite, at least from the perspective of simples and projectives, it's very straightforward in the case of a P.
Right. For example, for our client 4 group, we just have one simple and one projective indecomposable, but we had infinitely many indecomposables.
Yes, yeah. So the projective indecomposables can be classified. There's only one of them for a B. But the arbitrary indecomposables could be,
Who knows?
who knows?
Sorry, can you repeat the argument just on the right really quickly?
Yep, so
P is, so P is a projectile of some copies of the trivial.
yep,
And so
As-
is Q.
as is Q, which means that this has a dimension, at least 2, because P has a map to the trivial, Q has a map to the trivial. It's a direct sum, which means we've got at least 2 dimensions worth of maps to the trivial representation. But this space is 1 dimension, because it's determined by where it sends the identity in a 1-dimensional space. So I could talk about growth in deep groups. Maybe in the interest of time, I will give an example. Actually, no, I'll talk about growth in deep groups a little bit, and possibly talk about them more next time. If we need more. So growth in deep groups is one of these things which are like kind of like they are a way to simplify a category in a massive way. So they are a massive simplification, but they're a bit like weird the first time you see them. So the idea is A naught of some abelian category, say, equals the free abelian group on isoclasses of objects. Objects, so we'll denote them by this, subject to, so that means if there's X, so if we have a short exact sequence, then we set the class of Y, the class of Z, plus the class of X. Okay, so the way you want to think about this is like, take any object, break it up into its pieces via short exact sequences. So break it up into simple pieces via these. Those simple pieces and their multiplicities are what the growth in deep group remembers about that object. So it forgets a lot of stuff. So for instance, I think this is best as an example. Let's look at a cyclic group of order P in characteristic P. So I'm going to write, we're going to consider modules over this. So I'm going to write it in this way. Okay, so where X is a generator, this is just a presentation. But now we're in characteristic P. So that means X to the P minus 1 is the same thing as X minus 1 to the P by the Frobenius map or the central binomial coefficients vanishing. In other words, this ring, you've adjoined one element, and then you set its P power to be 0. So I'm going to write a filtration of the regular representation, or of this projective module, as powers of ideals. So we've got this ideal, and then we just take powers of it. Okay. And let's say we wanted to compute the class of this in the growth in deep group. Okay. And now this example is possibly too easy, but it sort of illustrates the point. Start with this submodule, take its quotient, you get 1. So that means the class of this is equal to the class of this plus the class of this. Let's say we have X minus 1 squared next. The quotient will also be the trivial quotient. So the class of this is the class of this plus the class of this. And again, and so all of these subquotients are the trivial module, which tells us that we can break this up via submodules and quotients into P copies of the trivial module. So the class of this projective equals P times the class of the trivial module. And you can imagine for more complicated representation, you might need to be clever about this, or it may not be obvious, how you can break it up. You always can break it up, because you could just say, for instance, take a simple submodule, then take a quotient. Then take a simple submodule of that quotient, take another quotient, and so on, until you've sort of decomposed it into simple pieces. So now, the most important thing for us, well, does anybody have any questions about that definition?
But so in that definition, are Y and Z also objects in this, or the ISO classes of Y and Z, are they also in this free Boolean group?
So objects in A. So like you look at the massive abelian group where free on the list of all the isomorphism classes.
But like all three of those objects in the short exact sequence are part of it. It's not just X.
Yeah, it's on.
So that's a short exact sequence in A.
Yeah. Because the X is used twice.
Oh yeah. So sorry. Yeah. So maybe I should say. What about you? Yeah. So it's on all the objects such that if you have a short exact sequence, the middle one is the sum of the other two. So a way of thinking about it is, force all of your short exact sequences to split, and just remember what isomorphism class you have, or in other ways, turn short exact sequences into sums.
And then you just take the free Boolean group of all those.
But it simplifies radically. So, here's the theorem, which isn't too hard to prove, which is that I will define this following Serre to be K naught of stations is free on the classes S for S simple. Okay, in other words, when you do this process, you actually just get a finitely generated Boolean group, which remembers the multiplicities of simple objects in all of your objects. And then again, I guess I'm working in an exact category here, but this is like the same growth and group, but for the projective modules. So projectives in rep G. And now this thing is free on the classes of the projective covers for S simple. And so we already sort of saw this, like this boils down to the fact that any projective is a direct sum in a unique way of projective covers of simple objects. Okay, so now this maybe. All right, it's 6 o'clock. So maybe I will stop there, but I'll just end with a motivating question. We have a natural map from projectives to simples, which just says, given a simple, what are its composition? Given a projective, what are its composition factors in G? For instance, in this example, we took this projective. It had p copies of the trivial representation. Right. This was an easy example because we only had one projective, we only have one simple representation. And one could, for instance, check that the dimension will tell you all you need to know. But in general, what is the question is compute C. So given a projective or given a projective cover of one symbol, how many copies of another symbol show up in its class and growth group? And so this question will be occupying a lot of time later, and is a very central place in the theory, in that you've got these key players, your simples, free Boolean group on the simples, the projectives, how do they relate to them? We know a little bit how they relate by this projective cover relation, but it's complicated. Like, this is a complicated matrix in general.